Okay, so a little diversity in the slides just for your visual impairment. So we want to talk a little bit about uncertainty issues, and the way to start that is just to review for a couple minutes the IPCC good practice guidelines. All right, next slide. Okay, two IPCC good practice guidelines that we need to keep in mind. Either over or under estimates so far as can be judged, and uncertainties are reduced as far as practical. Let's look at each one of those in just a little bit more detail. All right, next slide. Okay, the first one regarding neither over nor under estimates, essentially it says we want to use unbiased or at least nearly unbiased estimators. But let's be sure we understand what unbiased means. Unbiased means we're dealing with an estimator of a population parameter, something like mean biomass per unit area. Now, unbiased means that the average of all the estimates you could obtain with that estimator over all possible samples of the same size obtained using the same sampling design equals the true value. So it means you need a lot of samples, not one sample with a big sample size, but multiple samples, and you need to know the true value. Okay, next slide. Okay, the issue is that unbiasedness or bias is not a property, it's a property of an estimator, not an estimate, not a prediction, not a map, not a model, not a sample. I cringe every time I review a paper and I hear reference to an unbiased estimate. Well, what does that mean? What does an unbiased estimate mean? That it equals the true value? Well, how do you know if you don't know the true value? And if you do know the true value, why do you need an estimate? So let's be sure we understand what biased and unbiased means. So with the IPCC good practice guideline, we want to use an estimator that's unbiased. That means on average, it gives the true value. However, next slide. Even with an unbiased estimator, the estimate for a particular sample may deviate substantially from the true value. That's why we want to do uncertainty assessments. And that's why we have the second guideline. So next slide. Okay, we want to reduce uncertainties as far as practical. That assumes, it presupposes that we first correctly and rigorously estimate uncertainties. We want to talk about that just a little bit here today, because this guideline is not particularly well understood. We have two approaches to doing that. Two approaches to assessing uncertainties and to some extent map accuracy assessments. One which are called design-based estimators and another approach called model-based estimators. With design-based estimators, maps are auxiliary data, and we have a probability sample of reference data. Okay, the estimate is based on the reference data. The only role of the map is to increase the accuracy or reduce the uncertainty. The nice thing about design-based estimators is that they're generally unbiased. The uncertainties are easy to estimate, and you don't have to worry at all about the accuracy or the uncertainty associated with the map. All of that falls out in the variance estimator associated with the whole design-based approach. All right, next slide. Okay. The other approach is what we call model-based estimators. With these approaches, the map is the primary source of information. We're not augmenting it with anything else. The nice thing about model-based estimators is that you don't have to have a probability sample. You can use it, and it's preferable, but you don't have to use it. And that makes it nice for areas in which you don't have an NFI, you don't have any extensive ground sampling program. Okay, the disadvantage, the price you pay for that flexibility is that model-based estimators are not guaranteed to be unbiased. It doesn't even mean that on average you're going to get the right value. Now, if you have a good sample, if you have a good estimator, it's probably going to work out fairly well. The other thing about model-based estimators is that uncertainties, variances, may be very difficult to estimate because there's so many issues involved. All right, next slide. Okay, let's talk about model-based variance estimators a bit. Okay, remember, we're in the mode where we're going to try to produce estimates directly from the map. Okay, this may be the only choice when we don't have probability samples. Okay, model-based estimators, model-based variance or uncertainty estimators have two components: sampling variability and residual variability. Let's be sure we understand the distinction there. Sampling variability deals with samples, obviously. So if I take a sample and I use that sample to train a calibration technique or to train anything related to the mapping process, okay, that sample is just what it says. It's a sample. It's not a census. It's only a representation of what's happening on the ground. In fact, if I went out and got another sample, my calibration of my prediction technique, my mapping technique would change a little bit. And in the process, all of the map unit predictions, all the map unit values would change a little bit. A key point, there are two key points here. First of all, any mapping procedure that uses a sample or uses any product based on a sample has sampling variability. The bad news is that sampling variability dominates residual variability. Residual variability is just the comparison of map unit values and some kind of reference data. So when I hear people talking about maps and they've estimated the standard deviation of the uncertainty, I really ask, how did they get that? Is that just based on a comparison of a map unit value and a NFI plot observation for that map unit? If so, that's residual variability. And if the entire uncertainty assessment is based on that residual variability, it's woefully underestimated because the sampling variability is what you really need to get at. And that's somewhat difficult to do. That's why model-based uncertainty assessments are difficult. Okay. Now, not only that, but to estimate the overall uncertainty of a map consisting of multiple map units, I not only need the uncertainty for particular map units, but I need pairwise map unit covariances. The issue here is that if I obtain a sample, calibrate the mapping prediction technique, produce a map. Now, if I go get another sample and do it again, okay, all of the map unit values are going to change together. And because they change together, they're correlated. All the map unit values have covariances. And to get an accurate estimate of the uncertainty for an entire large area or subset of the map or for the entire map, I not only need to know the sampling variability for individual map units, but I need to know the sampling covariances for pairs of map units. Again, model-based variance estimate isn't easy, but usually what I see in the literature is that it's done simply using the residual variability, and it's a gross underestimation. Next slide, please. So model-based variance estimators, sometimes we have a closed form analytical variance. That is a formula that we can use. But for these increasingly popular non-parametric and machine learning techniques like random forests, and some of them, there is no formula. There is no equation, no estimator for the variance. But the only approach is you have to use a bootstrap variance estimator. Now, we've talked about bootstrapping before, and we just have a paper that's coming out in remote sensitive environment of how to do that. Two big questions are, who does that? The map user, the map producer. The map producer has to do that analysis because the bootstrap approach requires information used to train the calibration technique. And only the map producer has that information. So bootstrap variance estimation has to be facilitated by the map producer. Another big question is, how many bootstrap replications do you need? Sometimes we see in the literature 30 or 40 times. A popular number is 1,000, but we're beginning to see some where people are showing 10,000, 30,000 are necessary. The big question is, If you're going to do bootstrapping, okay, you need to ask yourself, what criterion am I using to decide how many replications are necessary? Okay, again, we're working on a paper on that too, but it's probably a lot more than you would think. Okay, so we know how to do this bootstrapping business for relatively simple problems, but it becomes much more difficult for what I call hierarchical or cascading prediction techniques. So when I use a model to produce predictions at one level, and then use those predictions as predictor variables for another level, it gets complicated. So if my mapping technique is going to use predictions of height from another model, and then use those as predictors of biomass in the next level, okay, that's one of those cases where you have sampling variability based on a product based on a sample. So it's difficult to do this cascading effect where we propagate from multiple levels to different levels. So the bottom line, as I've said before, is map-based variance estimation, uncertainty assessment is a difficult approach, okay? And if at all possible, it should be avoided. If at all possible, try to do the design-based. Okay, next slide. So what's the solution? What's the conclusion? Find a way to get probability samples whenever you can so you can use the design-based approach. Now, I appreciate that that's a big statement. I know that in places it's going to be almost impossible, but well, I also know that increasingly tropical countries are developing and implementing national forest inventories. We should really encourage that because it's really the easiest and the simplest, most reliable, and the most accurate way to get uncertainty estimates that comply with that second IPCC practice guideline. Okay, that's the take-home message. Get probability samples whenever you can. All right, thanks, Richard.